Another type of strain that brings atoms in electron clouds in closer proximity is called angle strain. And remember, electron clouds are going to repel each other. So bond angles in planar cyclic alkanes tend to be less than the ideal angle for sp3 hybridized carbons. And these atoms in cyclic alkanes, which contain only single bonds, are all sp3 hybridized carbons. And an sp3 hybridized carbon should have an ideal bond angle of 109.5. Putting the sp3 carbons into a cyclic structure constricts the bond angle to the angles available to the structure, and we call this angle strain. A cyclopropane, which has 3 sp3 bonded carbons in a ring, is constrained to a 60-degree triangle of an equilateral triangle, 60-degree angle for an equilateral triangle, instead of 109.5. And so that is much less than the ideal angle for an sp3 carbon. We also have a and since the sp3 carbons are supposed to be 109.5 degrees apart, and there'll be less electron repulsion if the carbons are 109.5 degrees apart, bringing them within 60 degrees of each other increases the electron cloud repulsion and causes strain. The cyclobutane also has a significant amount of angle strain. It has an angle that is less than 109.5, and so it is constrained, and the electron repulsion is higher than when the carbons are 109.5 degrees apart. The structures that have little to no strain are cyclopentane and cyclohexane. Cyclopentane does have some strain, and we'll discuss why on the next slide. But cyclohexane, in what we call a chair conformation, first of all, let me say that cyclohexane drawn as a flat polygon is incorrect. If it is drawn as a flat polygon, the angle is 120 degrees between carbons. However, that is not what occurs. The carbons, 2 of the carbons bend out of plane above and below the ring. And this gives a staggered orientation so that the carbons stagger as in a line structure. We call this the chair conformation, and in this conformation, all angles for the sp3 carbons are the ideal 109.5, and the repulsion or electron cloud strain between the sp3 carbons is much less. For angle strain, one of the things that is encountering is poor overlap, which results in a weaker bond. A sigma-sigma bond should have good, strong overlap, and the best overlap is at 109.5 degrees. Angle strain results in poor orbital overlap, as shown in Figure B, and that results in a weaker bond and a bond angle that is less than 109.5. So it deviates from the ideal bond angle for sp3 carbons. Here is an example of cyclopropane. Not only do we have the angle strain from the eclipsed carbons being closer than 109.5 degrees apart from carbon to carbon, but if you look at the hydrogens, and we do a Newman projection, you will see that the hydrogens on adjacent carbons are eclipsed in the eclipsed conformer, and they cannot rotate out of the eclipsed position because single bonds that are in a ring cannot rotate. So it is locked in the eclipse conformation and has steric strain from the repulsion of the electron clouds of the hydrogens. In cyclobutane, the hydrogens are also eclipsed. The ring puckers out of the planar arrangement, making this diamond shape in order to relieve some of the angle strain. But the hydrogens, circled in purple, are still eclipsed, and so there is still, in addition to steric angle strain, there is steric strain from repulsion of hydrogen electron clouds. In cyclopentane, we have shown in red 4 atoms that are in the same plane and 1 atom shown in green that is above the plane. We call this the envelope conformation. Think about when you mail an envelope at the post office. Before you put your letter inside of it, you have your flap that could be sticking up, and then you have your pocket. So we call cyclopentane the envelope conformation, and this is the most stable conformation of cyclopentane, but it results in less angle strain, so the angles are 108, but it still has eclipsed strain for the hydrogens circled in yellow. The relationship between the yellow hydrogen and the, let's do different color, navy. So between yellow and navy, circled in navy, this is staggered. So we have fewer eclipsed hydrogens, which results in less strain. Than in the other ring structures that we've already looked at. And then we get to cyclohexane. We are going to be dealing with chair conformer of cyclohexane a lot. The chair conformer of cyclohexane has the staggered orientation for all carbon atoms. This means that carbons that are directly adjacent to one another are staggered, and there is not eclipse strain from directly adjacent carbons. There is, however, eclipse strain between carbons that are 1,3. So if you look at carbon 1 and carbon 3, you will see a hydrogen sticking straight down. And those hydrogens, the electron clouds are close enough to have some electron cloud repulsion. And so they are said to be eclipsed. This is easier to view when you look at the chair conformer in the Newman projection in the middle top figure. In this Newman projection, you can clearly see the hydrogens between that are 1,3. So not only is hydrogen sticking down on carbon 1, 1,3 to the hydrogen on carbon 3, it's also 1,3 to the hydrogen on carbon 5. So you can see that those hydrogens are directly in line with each other, and their electron clouds can interact. The bond angles in cyclohexane are 111 degrees, slightly more than 109.5, but still stable. And all adjacent, directly adjacent, so 1-2 relationship carbons are staggered. To draw the chair conformer, this is something that you are going to have to do, especially in lab tomorrow. You're going to draw two parallel lines that are offset. So one should start way ahead of the other, but they should be parallel. You can then draw a parallel line that is going up from their position, and I'll circle it in green. So this parallel line circled in green is parallel to this other line. So I can add those in. And then we have a parallel lines that close the two ends, which I will circle in blue. So we have a series of parallel lines that we can draw that show in order to obtain the chair conformer. And you will have to be able to do what we call a ring flip, which is drawing the structure in the reverse direction. So notice that I have changed the direction of my initial parallel lines. And then my second set of parallel lines, I will change those as well. So in this case, I will have a line coming up over here and a line going down over here, although it probably needs to be at a steeper angle. Hey, hey. Oh, okay, we're gonna have to close, keep, blah, blah. There we go, okay. Big picture. Going back now, green. Drawing up here and down here. It's getting irritating. Seriously? Seriously. Okay. Let's just do it here. Draw. We'll pick green. Okay. So draw this up and perpendicular and parallel to the one on the other end, and then no, something is not quite right. Okay, instead of doing that, I have to think about this for a minute. Usually I just, throw it out there. I'd just be like, do, 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 do. Hey. Oh, picture might be quitting on us. It's not behaving. Okay, are you still recording? Yes, good, okay. Boom, 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 boom. Okay, so what I need to do is to go up right here and down right here. So what that probably means is that this line is not long enough and this line is not long enough. Then I can finish it off in blue, going down and down the two parallel lines. So we have to be able to draw it in both methods, connecting it this way and in this way. You can tell that it's much easier for me to draw in this orientation than in the other orientation. If you get enough practice though, you'll be able to draw both types very readily without having to draw the individual parallel lines. Okay. Axial and equatorial bonds on the chair conformer. Axial bonds are bonds that stick straight up, and they have specific positions and they alternate. Notice that these are staggered, so they're anti and 180 degrees apart. Completely vertical, and those are the triangles, showing that a triangle is where an atom would be bonded. 3 of the carbons will have hydrogens that stick straight up, and those hydrogens will be 3 atoms apart. And then atoms that are 2 atoms apart, one will be straight up and one will be straight down. If you look at the corner of the cyclohexane here looks like it is pointing slightly down, and the hydrogen goes straight down. If you look at the top carbon, it looks like the corner of the cyclohexane in the chair is pointing up, and in that case, the axial hydrogen goes straight up. Again, if the vertice of the line is pointing up, the hydrogen in the axial position will be straight up. If the vertice of the 2 lines intersecting on the cyclohexane is pointing down, the hydrogen will be pointing down. So we can differentiate and remember how to fill in our axial hydrogens if we pay attention to the direction that the vertice of the 2 lines intersecting points. Okay, if you fill in the other bonds, because each carbon in the ring should have 2 bonds to hydrogen, the other type of bond is shown by the circles in the structure at the right. And these bonds in red with blue circles are called equatorial bonds. And they are either slightly less than horizontal or slightly more than horizontal. If they are slightly more than horizontal, as shown by the carbon at the bottom left of the figure, then that hydrogen is considered to be above the ring. If you are slightly less than horizontal, as shown by the carbon at the top left of the figure, then that equatorial bond is considered to be below the plane of the ring. And on any individual carbon, if the axial hydrogen is straight up, then the equatorial hydrogen will be down or less than horizontal. Okay? And we need to know that in order to designate cis and trans conformations of the ring. We could translate this into a flat cyclohexane structure that doesn't show the 3-dimensional shape. And what you would have is that carbons that are strictly adjacent would have, for example, if the axial hydrogen, the red triangle, is above the ring, then on the next carbon over, the hydrogen above the ring will be an equatorial carbon because it staggers. So if the axial hydrogen on one carbon is above the ring, then for the carbon directly next to it, the hydrogen above the ring has to be equatorial. So it should flip. Axial is up, then equatorial is up, then axial is up, then equatorial is up, then axial is up, then equatorial is up. And you can see that in the figure that has both the triangles and the circles, where we are alternating axial up, equatorial up, axial up, equatorial up, axial up, equatorial up. And so it alternates on which of the bond types is above the ring from directly adjacent carbons. As I said, you should be able to perform ring flips. If you do a ring flip, you have to make absolutely certain that you transfer your carbon numbers correctly. Okay, so note carbon 1 to carbon 1. When we do the ring flip, the position at it almost appears that the position at which the carbon is has changed, but it has not. If you build the three-dimensional structure, that will become more clear. And we'll talk about ring flips in lab tomorrow. When you do a ring flip, the axial hydrogen on carbon 1 becomes an equatorial hydrogen. And we can highlight that in, well, that was not the highlighter. Let's highlight that with yellow. So the yellow highlights show an axial hydrogen that is a triangle. When we do a ring flip, it becomes an equatorial hydrogen that is a triangle. But it is still above the plane of the ring. So you can change between being axial and equatorial with a ring flip, but the side of the ring that the hydrogen is on does not change. If it's above the ring when you do the ring flip, then it will still be above the ring after the ring flip. Okay? The boat conformation of cyclohexane, this is a less stable conformation of cyclohexane in which, and it is less stable because there are more eclipsed hydrogens. If you look at the Newman projection for the boat conformation, you can see that virtually all of the hydrogens that are adjacent are fully eclipsed, and that means that there is higher steric strain due to electron cloud repulsion. This is an image of the conformers of cyclohexane. The only ones that you really need to know about are the chair and the boat. And half chair and boat are eclipsed conformations. Chair and twist boat are staggered conformations, but the twist boat is very unstable. I will finish this on a new video.